Okay, welcome everybody. Today we want to have Ayrton Nascimento. He's a PhD student from Universidade Federal do Rio de Janeiro. Sorry for my pronunciation. So he's going to speak about a proton structure function F2 from a holographic Einstein-Scalar model. So Ayrton, all yours.
Okay, thank you, Lucas. Thank you for inviting me. Like you have been asking me a long time ago, but I finally got the chance to give a talk to you guys. So yeah, like Lucas said, I'm gonna talk about this. I it's not like most of the guys in the group they have like some more old other holographic stuff related things, and I'm going to talk about some particle physics related theme based on holography. So this study, I'm gonna tell about the F2 function for the proton, which I'm gonna tell you about right now about what is all about about uh, this thing over here. Let me see. Okay. Oh, oops. So yeah. So for this, I'm gonna need to talk about like deep inelastic scattering first. So I'm gonna review some important things about this thing. And then I'm gonna tell you about some holographic models used for describe this DIS stuff I'm gonna tell you right now. And then I'm gonna tell about the specific model I used to describe this deep inelastic scattering, how is it's related to the quark gluon plasma, because it's a model that is more used for this kind of stuff. And after that, I'm gonna tell you how I apply this model to the deep inelastic scattering problem I'm interested in. Okay, so starting right now, what is the deep inelastic scattering, right? So we have some collision between a lepton. It could be like either electron or a muon colliding with a proton in a collision. So like this collision happens with exchange of a virtual photon with momentum q, right? So like depending on the energy you give to the system, like the energy you give to the electron beam colliding with the proton, you can have like a final state of particles, which I'm gonna call X over here, which can be like you can literally break up the proton, and you can have like the final state. You can like measure like the final electron, and you can have information about this final state X over here, which describes like the particles that are inside the proton. Okay, so some here are some kinematic variables for the problem. So P is the momentum for the proton, Q is the photon momentum, and this W here is gonna be the like the mass of the final state X over here. I'm representing here. Okay, so, and also I'm going to describe like this problem in terms of two parameters of interest. Like for us theorists, like the more interesting parameters are the q squared and the x parameter here. Like the q squared is just the capital Q square, just this minus Q square over here. And this x defined like in this equation over here, it's a parameter we call the Bjorken X, which describes like the inelasticity of the problem. So like if we have like elastic scattering, you can just have this W like the mass of the proton over here, and you just get one over here. So this X has like one for the elastic regime. And if you get like a final state in which like this mass is bigger than the mass of the proton, like you have like right away an inelastic process, right? Because this thing over here is gonna be less than one, and these are the limits of this parameter here, this Bjorken X. It goes from 0 to 1, and it describes like how inelastic is the process, or how elastic it is. Like it is, if it's 1, you get like elastic scattering. If you and less than 1, you get like inelastic scattering. But like the regime in which we have like inelastic scattering, deep inelastic scattering, is in which you have like this energy for the like the exchange momentum over here related to the photon. If you have like this energy bigger than 1 GeV squared, you have like deep inelastic scattering because like 1 GeV squared is the mass of the proton. So if you have energy bigger than that, you can like probe inside what is inside the proton, right? So you can like break up the proton and investigate what is inside of it, okay? So this is basically the basic information about the deep inelastic scattering I'm interested in, and is the information that is going to be like relevant for us in this presentation, right? So how to like right now I'm going to tell you how to describe this in holography, right? Because like not right now, but like for describing the cross section, it's not holography right now, but in a minute I'm going to tell you how to do that. But before that, the cross section related to this problem, like just kinematics, you can just the definition, like the cross section, you can calculate in terms of a hadronic tensor. You can have like another tensor in this process, but the one relevant for us is this W M mu given by 1. This is the hadronic tensor, and J mu is the quark current uh, related to the process. Okay, so we can like work this further out and certain a complete set of final states. We can write the hadronic tensor like this, like the equation 2. And here comes the something that's really interesting. Like for unpolarized beams, like you can also have like polarized beams, but for unpolarized beams, you can work out like this expression too for this context, and you get like let me just okay. So you can for this case of unpolarized beams and targets, you can work out this expression and write like a general expression for the hadronic tensor, like the equation 3, in which I have like uh, some like functions over here, f1 and f2. So what are these functions? What do people get about it? What they tell you about the process of deep inelastic scattering, right? So people in the early like late 60s and early 70s, people starting to do experimental studies on deep inelastic scattering, and there was a concept that was devised back then to help understand what these f1 and f2 functions are all about, okay? So this concept people theorists were devising back then. um, like all this stuff I'm telling you right now, people starting doing even before the concept of QCD. Like even before QCD was invented, people starting studying these processes and like devising like concepts, theoretical concepts to help understand like what this f1 and f2 functions are. Okay, so back then, like I'm just okay. So back then, people starting like creating this concept of partons, which nowadays we know as quarks and gluons, but back then people didn't call quarks and gluons. They just gave this name partons for what is like inside the proton and also like the neutron, okay? So this concept helped like us understand what these destruction functions are all about. So say that the proton is made of some particles inside of it, and the deep inelastic scattering process actually is a process in which the photon, which is the virtual photon, which is exchanged here, it hits some of these particles inside the proton, okay, and it deviates this particle over here. So say that like the proton carries momentum p, and this particle inside the proton carries a part like a fraction of its momentum, like c p over here, right? um and okay, so you can construct like a kinematics like this, in which like the final like the final momentum after the collision of this particle, the parton over here, is QP plus Q, like the photon momentum over here, which is exchanged. And you can just work this out. And like this is the momentum after the collision, but you can also notice that the momentum after like before the collision, like the momentum of this parton over here was just QP. And then like this momentum squared is just like the mass of this parton, which I'm gonna call like MQ over here, okay? Which is the same like the final mass, like the mass of the parton doesn't change. So you can conclude that this middle term over here is equal 0. And you can conclude further that this this parameter over here, which I just call the fraction of the momentum carried by the parton, which is a gluon or a quark inside the proton, it actually is the same expression for the Bjorken X, which describes the inelasticity of the problem. So actually, functions that depend on X can actually depend on the fraction of the momentum carried by the particle inside the proton. So what we can conclude about it is that these functions over here, f1 and f2, they carry information about how is the momentum distributed inside the proton. So this is really nice because it gives us information about the internal structure in terms of quarks and gluons. Back then, people didn't call it like quarks and gluons, but we can like see nowadays how these functions give information about the internal structure of the proton, like the distribution of momentum inside a proton or a neutron, how is it's distributed inside. And all of this I'm saying right now is about longitudinal momentum, okay? We can have like transverse momentum, okay? But then you have to work other structure functions for polarized beams and everything, you get something like this. Or other concepts which is like transverse momentum distributions and everything, which are more modern stuff, modern concepts. But these are I'm not going to talk about right now. Just longitudinal momentum information I'm interested in right now. And back then, like people have like these, like most of the modern experiments, like they have like this whole range of values for F2 against Q squared for different values of the Bjorken X, for different values of the fraction of momentum carried by the particle inside. So you have these different behaviors over here, like for different values of Q and X. So you have like this picture in the right over here, like in general, okay? So you can have like an F2, uh, you can have like F1 and F2, but I'm interested right now in F2, which is it's more related to things related to momentum distribution than F1. F1 is also related to that, but it's more related to magnetic stuff. Like F2 gives information about electromagnetic interaction in everything. And that's why I'm interested in F2. So we have
Uh,
this behavior. Okay. Oh, sorry.
yeah, so sorry, Ayrton. This thing F12, you will if you go to CERN, you will always be at x equal 1, right? Because it's fully inelastic.
For inelastic, it is like less than one.
Ah, less than 1.
Yeah, yeah. One is like elastic scattering.
But when you go to high energy, you will see x less than 1 or more close to 1.
No, no, they are like independent stuff. Like as you can see here, as you increase the Q squared, like the energy, you can have like different behavior for each value of X. So you investigate this behavior on high energy for different values of the X parameter over here. You can say like you start the biggest one is 0.85 over here, and you can just all the way down to like 0.000063 and everything. Yeah. So
Oh,
you
okay.
see, they are independent stuff right here. for a specific value like 10 to the third, you can have like all these points over here which describe different x values. You see?
Ah, okay. Okay,
Yeah.
okay, thank
Okay. So yeah, this just the general picture. You can have like this behavior over here, this one, and this one. Like okay, so these behaviors are gonna they happen, and the different models you can construct for this, they can display this one of these behaviors over here. So what I'm gonna do right now is just to describe some models which I've been studying and like the past year until now, and I'm gonna show you what behavior do they have like in comparison to this. Okay, one of these behaviors are going to show up in the holographic models I've been studying. Okay, so how to connect this to holography? Polchinski set a prescription for that, like in 2000, like the first years of the millennium. I have that reference at the end, but Polchinski was the first one to do that for holography, like the first model that came up was the hardware model, right? And he did that for the hardware model. So the prescription goes like this: like you have this matrix element over here. This matrix element, if we go back here, let me just go back a little bit. It's inside like the hadronic tensor, right? So Polchinski set this prescription for the hardware model, and it is just like an interaction action over here. But instead, it's not a simple interaction action, it's an interaction action in 5 dimensions, okay? Like in the 5 dimensions of the anti-de Sitter space. So you just have like the fields for you have the photon field over here, and you have some fermionic fields over here, okay? But given this, some people starting to work out like the holographic models, with this prescription, right? So some of them were like the software model, the 3D7, the hardware model itself, Prosinski was the first one to do that. But the thing is, like models like software and the 3D7, some people did that for the deep inelastic scattering problem, but the problem is that they didn't do that for to include fermions. They have like imagine you have like a deep inelastic scattering. Let me just go back a little bit over here. You have this problem over here, but instead of a fermion, like a proton, you have a scalar field. So these models like the after like Polchinski, people starting to do that with scalar fields. So imagine a photon interacting with a scalar field and everything. So you didn't have like a real okay, you can have like a scalar field like the Higgs field, for example. You can imagine some crazy deep and elastic scattering of the Higgs field. Maybe, I don't know. But the real thing is like you have deep and elastic scattering with fermions. But these first models didn't have like this for fermions, just the one Polchinski did for the hardware model. Okay. But some later models did include fermions for deep and elastic scattering. And some of these models, people in my group in Brazil, they did this for deep and elastic scattering. And these are the ones I was inspired to do the work I did that I'm going to talk about in a few minutes, okay? So the models I was inspired were this one, the deformed ADS space model and the modified software one. I'm gonna show you right now how they did that for deep inelastic scattering. And after that, I'm gonna show you other model I used inspired by these ones, okay? So how do you do that for the deformed ADS space? So have like an action for some particle you are interested in. So which is like this. And here you have like a 5-dimensional action in which you have like the determinant of the metric of the ADS space you are working with, which is this one, 8 over here. And it's not like the usual ADS space, it's ADS space with a factor over here, an exponential factor. in front of it that deforms the ADS space, okay? And this factor, this function A of Z over here, it goes like this, okay? So this first term over here, if you work with, you just get the usual ADS space, but it has like this additional term over here with this K, which has dimension of mass squared, okay? Depending on the Z coordinates, like the holographic coordinate Z, okay? So how do you do like the deep inelastic scattering in a problem like this? Okay, so you have the space-time, okay, and you are going to work the fields inside your Lagrangian for this space-time, okay? So you use again like Posinsky prescription, in which you are going to need the photon field and the Fermi field. So let's work out each of one separately, okay? So you have a photon field over here, given by an action for the photon field, and you have to work this out, okay? So along this gauge fixing over here, you can like work the equations of motion from this action, and you get these equations of motion 13 and 14, okay? So if you consider like a photon that has polarization like a transverse polarization like that, and like this condition over here, for a photon in the, you want the solution in the boundary of the ADS space to be uh, like a wave over here, okay? So you impose these conditions, like transversality and this one in the boundary, and you can work the solutions for this. Like what you get is like, you just get one equation of motion is enough for you. Like this one, you can show that it's not needed for the problem with these conditions I just showed you, and you can just solve this equation 13 over here, and you get solutions like this. Okay, so we have like this solution over here, which is analytic. It's an analytical solution, which is nice, which is in terms of a gamma function and some spatial functions, like this U over here, which is called trichotomy function. Just a weird spatial function, but okay, so you have an analytical solution in terms of these functions over here, okay? So I would just call this gamma and U together, this B function over here, just to make things easier to work with, okay? So this is the solution for the photon. And if you go for the fermionic field, you just work with a Lagrangian, a direct Lagrangian in 5 dimensions, okay? So right now, the Dirac operator is defined like this, in which you have like all these things over here, like the gamma matrices and everything. And also you have this omega over here, which is related to the spin connections. Is something like it's necessary for describe fermions in 5 dimensions. You have to have like these things like this to describe fermions like in 5 dimensions in the ADS space, rather than a usual Dirac Lagrangian with Dirac equation and everything, right? So these are just some things related to this, and with these definitions over here, you can go back and write down the Dirac equation for the fermions in 5 dimensions, okay? So the equation you get is just this equation 20 over here, and you can make some other assumptions, which I'm going to explain later, but in detail later. And what you will get is like solutions like that, okay? So you have like these solutions over here, in which we have like this, we call this I'm just trying to remember right now, the spinors. You have the spinors over here, and you have like these functions over here, which have left and right chiralities, right? So I'm gonna tell about it later in detail, so you're gonna understand better with this. So these are the solutions for the fermion field, in which like Si and Xx are just the spin of the initial and final states, okay, related to these particles over here, which are the quarks I'm interested, okay. So you can just go back to Posinsky prescription and insert these fermions and photon field in the prescription, right, over here. And what you get is this, okay? So inserting the solutions here, you can work out like this action, and you can end up with an action like 24, which is given in terms of these integrals over here, I, L, and I, R, which are integrals of the functions of the solutions I have for the photon field. You remember like the B function over here and the fermion solutions over here, okay? So you can just have this final form over here in terms of these integrals, okay? So when you work out this, you can just go ahead and do some algebra for the hadronic tensor, and what we get is a function like is a hadronic tensor like the one given by 26. Okay. So this allows you to extract like the actual F2 functions compared with the general form for the hadronic tensor in terms of F1 and F2. So you can just read off immediately the F2 function from this. And what we get for this model is just this equation 27 over here. So you get an F2 function which is given in terms of these, like the x over here, the Bjorken x, and this mx over here, just the mass of the final state, okay? Uh, and then like this one is like, we can just work with this one in the model, like in the, doing the computational part of this problem. And people did that in terms of these integrals over here, okay, for this model. And what did they get was this picture over here. It's given in the references. It was one of the guys that did his doctorate, his PhD in my university, worked in my group and everything. And he wrote a paper on this problem, and what he got was this one, okay? So you have this like the F2 function in terms of q squared for different values of x. Like the values he did work were the 0.65, 0.75, and 0.85. So here are the how the model works for different values of x in terms of q squared. So you see that the best one, like the model works best for 0.85 for a high value of the x parameter, okay? But this thing over here was done like just fitting the model to the experimental data. So you have like to work in these three parameters here, like this G effect over here, the mass of the final state, and the like the parameters inside the integrals. You can just work these parameters just to fit the experimental data. And the best one was given by 0.85. Like for the other ones, you see that they are not that good to describe the F2 function for these values of x. Uh, the experimental data you have available for you for these values, okay? So another model I'm going to talk to you about is just the soft wall model and the modified soft wall model. I'm not going to spend like much time on this because I have already told you about other model. So basically the thing is like the soft wall model, you have like a Lagrangian like this and an ADS metric, a conventional ADS metric like this. Okay. But the thing is, when you work like a soft wall Lagrangian like this exponential factor over here for fermions, it gets factored out of the equations of motion. So like the equations of motion for the fermions, they don't see like this factor uh giving some influence on the equations of motion. So it's just like an equation of motion for a direct fermion. So they don't get influenced by this factor over here. But you want that. So this was a difficult some issue people have had like when describing software model for this problem. So what people did for this was to implement like a Lagrangian like this, in which beyond the photon, the electromagnetic terms over here, and the Dirac Lagrangian over here, you get a term which interact with the fermions like this. We have like a mass. This mu over here is the mass of the fermion in the bulk, in the ADS space, okay? And you have like this function over here in the mass term, which is a function of the z coordinate. So why do people did this? People did this because like we know that in the ADS-CFT correspondence, like the mass of the operators we are interested in, like the mass of the operators, they are related to the like the mass of the fields. I'm sorry, the mass of the fields we're interested in, they are somehow related to to the the conformal dimension of the operator in the bulk, right? In the boundary of the ADS space. So yeah, so in this conformal dimension of the operators in the boundary of the ADS space, we know that in some models, in some holographic models, they get like some corrections, like anomalous contributions to this operator, to the conformal dimension of the operator, right? So the thing is that these anomalous dimensions, they are related to the energy scale of the you are probing the system, and we know that the z coordinate, one of the interpretations of the radial coordinate in the holography is that the z coordinate in ADS-CFT is related to the energy scale you are probing the system, right? So this is why people like devise the a Lagrangian like that, so that you have some function of the z coordinate. So you're gonna like the fermions will be sensitive to the scale of the system, to the energy scale of the problem. Okay, you are investigating the fermions like in the deep inelastic scattering, for example. So this is why people did this for the soft wall, in order for the fermions to have some influence on the energy scale of the problem. Okay,
I don't know.
and
Say
yeah.
sorry. Sorry. Yeah. So you're adding this software because what didn't match before was the UV, right? The air was okay, but the UV was far away from the experimental data, right?
UB, what is UB?
In the high energy limits,
Oh,
in the
okay,
graph
okay.
you showed
Ah, okay.
before,
Uh-huh,
uh,
uh-huh.
in the UV that will be near to the ADS, to the boundary of ADS. You have to modify that or something like that. This is why you are adding a software. So you are
Yeah, people
modifying.
did people
Yeah.
did this because like you didn't have like the fermions to like the equation of motion for the fermion. They didn't feel this factor over here. So this is why you didn't get like a good description in the soft wall model for the deep inelastic scattering, for example. So and also if you just did like that, an action like this, and you get the equation of motion for the photon and for the fermion, people didn't get like a discrete spectrum for the particles. You see,
Mhm.
so like a model like this, a holographic model just like this soft wall, you don't get a discrete spectrum for the particles. So that's a reason that people had to modify this model in order to get a discrete spectrum for the particles involved.
Okay. But usually ADS discretize the energy automatically.
Yeah, I know.
What's
But
happening
people did
here that that doesn't happen?
uh right now I don't know the details to tell you the truth, to be honest with you. But like the papers that I was like reading, they were like saying that like the model like this, when
Hmm.
applied to a deep inelastic scattering problem, you
Hmm.
get the equation of motion in everything, and you solve the equation of motion to get like the masses of the particles. you don't get a discrete spectrum for this model in specific.
Ah, okay, 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 okay.
Yeah, like the other one, the deformed ADS space, it's everything okay. You don't have those issues there.
Okay, okay, okay,
Just
okay,
in the software model, you get this.
okay, okay. Thank you.
So, yeah. So people have to modify this. But this is just for fermions. If you go for mesons or something like that, you don't have this problem. This is a specific problem for this problem over here. And and also like the potential goes like this, okay? And you can just work out the solutions and everything, the interaction action over here, like 32. And you get the solutions for the photon, like just before. You get the solutions for the photon field, the fermions and everything. And you can work out the hadronic tensor and you get the F2 function, right? So Nelson and Alfredo were some guys that worked together in my group in Brazil. And they got like this modified software model and they get an expression really like similar to the one for the deformed ADS, but the values over here are a little bit different. You don't have like the mass over here, the final state involved. So it's similar, but it's not the same. But still, they get like this behavior over here for the F2 function for x equals 0.85. So they get like these different lines over here. These are the points are the experimental data, and the lines are just different versions. Like you can just get the free parameters involved in these integrals and everything. You can just turn them, uh, modify them, you get different lines over here. But all these lines with the different parameters involved, you just get a behavior like this for this model, okay? So these are some examples of holographic models used to describe deep inelastic scattering, okay? And right now I'm gonna tell you about the Einstein-Scalar model, also known as the Einstein-Dilaton model. It's more known as
Ayrton,
Einstein-Dilaton, but
sorry,
yeah.
before we change the topic, so in the previous graph, with all you told us, it seems like the holographic model works better when it's less deep scattering, right? So
Yeah.
0.85. Okay, so isn't this like a problem? I mean, you start at the beginning. Doesn't need to go. We don't need to go to there, but you say that we start with the an ADS deformed space, right? So my question is, okay, maybe I'm thinking like in a perturbative way. Okay, we know that if it is less elastic or elastic, sorry, deep scattering, sorry, work uh, well, fine. Why don't take like higher orders the formation ADS, the ADS space, or I don't know if you have sense this, because I mean the graph looks like that, like if you consider like a small deep scattering works fine, but if you go like more deep, it starts to works doesn't work very well. So that's like my question. It's not like we have to take more like higher orders of the deformation on the back or something like that. Or maybe I got a bit lost.
Like over here, you say like the deformation goes like this. You mean like
Yeah.
if I just expand
Yes.
this function over here, this explanation of this k over here, because you're gonna get like an explanation of half k z squared, right? You mean like if I do like in a perturbative expansion, a Taylor expansion in this, and
Yes.
see how good it goes. Yeah, we actually thought about it, the same thing you thought, my advisor told me why we don't do that to see how well this describes the same results over here for this model, like this one, because this
Mm-hmm.
model over here, until this point, over here with the integrals, it's just analytical. But
Okay.
the thing is, you have to solve the integrals numerically to get the F2 function, and you don't
Uh-huh.
have information how, like a perturbative case and everything. You don't have information about that. You just solve numerically the integrals, and you just plot the F2 function, and you get this, right? And the
Mm-hmm.
thing is to think, what if we do like a perturbative procedure on this? How well we can get this? Well, I try to do that. Like before I present like the model I used, I try to do this, in this model over here. And I did it's not, it's somewhere, like I just have some notes on this. I didn't even talked about this with anyone yet. But the thing is, I did it a little bit here. Like
Mm-hmm.
I did like a Taylor expansion on this, and like for the first term, I tried to reproduce all these lines over here with just the first term of the expansion.
Mm-hmm.
And I didn't get any close to this, right? So the thing is,
Okay.
like, I have like a paper on which I do an expansion like this one you are you are thinking about, but I didn't apply the expansion to deep inelastic scattering. I just what I did was to investigate how well an expansion like this reproduces
Mm.
like the spectrum, the mass spectrum of this model over here, like this one. If I get forget about the photon field, like I have
Uh-huh.
photon field over here, but I have like the fermions. How well this model with an expansion describes like the modified soft wall model. I have a work on this, on this, the thing you are thinking about, but not specifically for the deep inelastic scattering. I was interested in the discrete spectrum of the two models. So you have
Mm-hmm.
this software model over here. You get the spectrum for the particles and everything. And what I did was to do like a perturbative like expansion on the deformed ADS space. And
Mm.
what I found out is that the models they're not exactly the same, but
Uh-huh.
they look pretty close to each other. Like the fine, like they differ on the spectrum of the particles for the two models. What I found out was that with this expansion, with just like the first term, like the quadratic term, you don't have to like to go to third order terms. Just the first term, the quadratic one. What do we get is like the spectrum, mass spectrum of the two models, they differ just in the ground level. Okay,
Okay.
that was the thing I found out. I can send you the paper. You can have a look.
Okay. Yeah. Okay.
It's really interesting. It's really nice to think about it. How what if we do like a perturbative like procedure here, and what do we get? Like
Hmm.
I found I actually did that, but not for the deep inelastic scattering, just for the spectrum of the particles.
Okay. Okay. Thank you, Ayrton.
Yeah. But for the deep inelastic scattering thing, I started doing that, but I didn't find anything any good at first order. If I go like obviously to sixth order, maybe I can get something similar to that. Okay.
Oh, so you
Because
abandoned because was too okay, understand. Okay. Was too
yeah,
difficult.
yeah,
Uh,
yeah, yeah.
too
I'm
many
gonna tell you
orders, too
about
many.
it. Yeah,
Yeah, yeah. When we start
yeah.
the record, you can say the truth.
Okay, yeah. There's so many ideas right now going on, but okay,
Okay.
yeah.
Okay.
So. Keep going with this. I'm going to tell you about other model I use, which is the Einstein-Scalar model or the Einstein-Dilaton model. So, like I was telling you about, I spent some months in the U.S. with another Brazilian professor there, and I just came to him with the idea to do deep inelastic scattering with these models, and he said, "Oh, look, I work with holographic models, not for deep inelastic scattering, but I work with quark gluon plasma stuff with this Einstein-Scalar model. And what about we do like the things you do in this model I use?" I said, "Okay, we can do that." But the thing is, why does he do that stuff with this Einstein-Scalar model? Because we know like deep inelastic scattering, quark gluon, this plasma description are all things of QCD that are things related to the non-perturbative regime of QCD. So that's why people use holographic models. People have like Lattice QCD and everything, but the holographic approach is really nice because you have like you can do things in holography that get you some results like deep like the F2 function, the things related to quark gluon plasma and everything. And the QCD doesn't work really well. We know about that, and that's why people do that. And specifically for the quark gluon plasma, so the thing is like the quark gluon plasma we know is a state of matter that is under extreme temperatures and densities, right? So you have like these informations over here, like just general information about the quark gluon plasma and everything. But the thing is, like as the quark gluon plasma is the QGP is a state of matter that works like is under extreme temperatures and densities, is a perfect scenario for the finite temperature description of QCD. Okay, so instead of doing finite temperature QCD, you just do finite temperature descriptions of holographic models to describe the QGP and everything. Okay, so this is like the motivation, like people start doing such stuff. Like the model, the Einstein scalar model is the one like with an action like this 133 over here. And this is done for finite temperature, but zero chemical potential. Okay. So people usually we use this model over here to describe the QGP because like the if you have like this is like the rich scale over here because it's somehow it's like inside of it you have like the metric tensor, and we know like but the holographic or like the holographic dictionary, we know that the metric tensor is dual to the energy momentum tensor. The scalar field, the phi over here, is related to the scalar glue ball operator in the dictionary. Okay, so you have a model which you can describe like you can you can have a model that describes the gluon part of the fields where you are interested. If you want to describe other degrees of freedom like quarks and everything, you have to add other terms over here which are more difficult, but this is the most simple one in which you have glue ball operator over here and you can describe gluons with this model. Okay, and also you have this potential over here which for the quark gluon plasma people choose this V of phi over here in order to match like lattice QCD results at zero chemical potential. So this potential is free. You can just like design a potential that matches the things you are interested in. And people, when they use like these this Einstein dilaton model, they use for the QGP stuff. They use this with this V chosen in a way to match the lattice QCD results. So and
Ayrton,
like for yeah, go ahead.
sorry, basic question. Can you
Uh-huh.
explain a bit more why you can use this model to study QCD and gluons?
Uh-huh. Yeah, the thing is that as I was saying like a minute ago, like people like when you try to do such stuff in QCD, yeah, you are in a regime in which you are in non-perturbative like regime of QCD. So you are not able to get a perturbative expansion and everything and work the stuff you are interested in. So people do that with these models, and people like, it's just like a thing, like when people do use these models, you get really excellent results.
So the
And
question, maybe the question was why people use these models? Maybe because it works. That is the answer.
yeah, because it's an
Because
like
it seems to
everything.
me highly non-trivial to propose something like this to study
Mhm.
gluons and QCD, right? I don't know
Yeah, I know.
why in principle, I don't know why they use these models, but
Um, yeah, I would say to you that it's an alternative. When people started doing that for like particle, like in the early years of holographic models applied to particle physics and other branches of physics, people started seeing that these models worked really well because you have like the ADS-CFT correspondence is a correspondence that relates a gauge theory in 4 dimensions, which with a gravity theory, classical gravity theory in 5 dimensions in ADS space.
mm,
This is the whole thing behind the correspondence.
mm,
And the thing is, you can describe a gauge theory in 4 dimensions using a gravity theory. So the idea was in the early years, why not describe a theory like, it's not exactly QCD, but if I assume that this theory is QCD, I can use this correspondence and use gravity actions and gravity theories to describe. If I assume that the correspondence is true, I
mm.
can just work all this stuff with gravity-like theories, like the one I'm doing right now. This is
Yeah,
the whole point of the correspondence. This is why it's so interesting, because if we assume this is true, I can work more, I can construct and devise models
you can
in the
like
gravity.
propose a model. You can propose a
Uh-huh.
model and see if it works.
Yeah, because the
Maybe people try
correspondence is
different
all about.
models.
Uh-huh.
Sorry, maybe people try different models, and this is one that reproduce some results, right?
Yeah, exactly. But the whole motivation is the correspondence, because you have like a gauge theory. It's not exactly QCD, because the gauge theory in the correspondence is conformal invariant. And
Yeah,
QCD,
yeah.
we know that it's not conformal invariant, you know.
You
But
mean
if you assume that
in like the original proposal,
uh-huh.
uh, n equals 4 Super-Mills,
Uh-huh. Yeah.
and then people try to use different QFT, right? For example,
Yeah.
the one that you're
Mhm.
working on.
Yeah, but these theories over here, these models, they're not theories, but the models over here, which the deformed ADS, soft wall model, and everything, they break conformal invariance. So in the original proposal of the correspondence, they have like an exact match between
Yeah,
gravity theory and a gauge
uh,
theory, which is conformal invariant. But all these
fine.
models over here, they break the conformal invariance of the model of the correspondence.
So
But
you can only do computation for one side in this case.
yeah, exactly. We
In
we,
the
we don't
case,
know how the side
yeah,
work.
okay, okay. In the case of Maldacena, you can do
Uh-huh.
both and see if it match. But
Yeah,
what?
Maldacena proposed, and he showed that you can have a relation between the two, but he did not. He did prove the correspondence for a specific case.
Yeah.
But what people do with these models, they don't know what
Mm,
is the gauge theory related to this action over here. We don't know that. We just assume that exists a gauge theory on the other side of the correspondence that's related to that. And I say, I not I like it's a huge point right now. I assume that this gauge theory, I assume that this is somehow QCD. I know for true that it's not QCD at all, but I assume that it is true, and I work everything on the gravity side. I don't know how it is on the boundary of the SFT correspondence of the DS space. I don't know which theory is this. I just
Hmm.
assume that it's somehow QCD. It's something really close to QCD, and I assume that and work the gravity side, and I see what comes out of it.
Yeah. Okay. Okay. That is why it's called a conjecture in this case, right? Yeah.
Yeah.
Okay. I
You're right.
understand the logic. Thank you.
You're welcome. So yeah, going back here to this Einstein-Dirac model, to describe it in finite temperature, people do that with black hole engineering, which is a thing really nice for finite temperature in holography. Because what people, I'm not going into details right now, but you can show that a gauge theory with finite temperature is related to a black hole. So you can say you can actually show that the temperature of the two theories uh, of the gauge theory and the temperature of a black hole of an ADS space like that, you can show that these temperatures are related. So that's how people describe finite temperatures problems in ADS-CFT. So they construct space-times like this, which is not ADS, it's just asymptotically ADS. Like in the boundaries, like if you have the like this, let me just explain. Like in these models, people usually do, they call the holographic coordinate the phi coordinate itself. So the phi coordinate is just the holographic coordinate itself. People just call this like this because this is more easy to work out the equations of motion. This is just the reason for that. But you have like a space-time which looks like the ADS, in which we have like this phi over here being acting like the holographic coordinate. And also you have like the horizon function over here, which like reproduces the black hole. Okay. So this black hole, it's not exactly a black hole. In the literature, people call this the black brane. It's some black brane over here, which has some temperature because it has a horizon and everything. And like if phi goes to zero, it leads to the ADS-5 boundary. Okay. So using this engineering over here for the finite temperature, you can get things related to finite temperature problems. So basically, what people do in like this A and B over here, not uh, they are not defined yet. The whole program of this problem over here is just to solve the equation of motion of this action 33 and with this space-time, and you get some equations of motion like that, like these ones, okay, for the A and B and everything. And what we can do in these models is to consider a function like A prime, like a function G. And with these equations over here, you can write down these equations for A, B, and H, okay? And the thing is, and also beyond these equations, once you have like these two sets of equations, you can work out a master equation for this g function over here, which goes like this, is 42. And once you give like uh, some uh, some boundary conditions for this differential equation over here. Once you give these conditions, you can solve this, and you can go back and solve for A, B, and H. So once you do that, you solve this equation, you determine the A, B, and H function, and so you can determine the geometry of the space-time you are interested in for describing your problem. Your and once you get that, you can like compute things like temperature and entropy and all things related to those thermodynamic functions over here. Okay, you can construct the equations of state and everything. That's what people do when studying the quark-gluon plasma and everything. And when people want to describe like beyond finite temperature and want to describe like finite chemical potential, people like add a term like this, in which you have like the electromagnetic tensor over here, which is coupled to some function of the z coordinate of the radar coordinate I just called phi over here. And you can go over that all again. You can just have a black hole over here and just have these functions, the electromagnetic field, like the A mu field. You can just say that it just has the time component, because this is gonna give you it's related to the chemical potential. That's why you assume like something like this. And you can work out things like the temperature and uh, and the entropy and things related to those stuff. So what people do and get about the QHP, like the quark gluon plasma, they get these models, like a model like this, exactly like this one. The professor worked with in the US, he used this model to describe the quark gluon plasma, and he got something like this, like equation like a QCD phase diagram, in which he investigates like this Q over here, which is like it's like jet, it's like energy loss in the plasma. You have like some, let me see other thing over here, like this chi2 over here, which is other thermodynamic function. And you have a lot of them. So people just calculate this stuff with this model, and they can describe things like this, like phase transition of the quark gluon plasma between these values of the chemical potential and temperature. So people can do stuff like that with these models, okay? And they get something really nice that they can describe things like this and phase transitions and everything. But I didn't go into details about this, but these are
Nathan,
the
ca- sorry, can I
okay.
just ask a little question about this? Maybe if you don't want to go more deep, it doesn't matter. But uh,
Uh-huh.
in the bike, um, I don't understand what's happening. I mean, you say that we were interested in the bike in a black hole because we need a temperature, right? The CST. So we have a black hole in the bike. So when in the plot you have a phase transition, you have a transition to what in the bike if you already have a black hole, or the black hole is the right part of the plot, and maybe I understand correctly.
I see. Yeah. Yeah, the thing is, I'm doing calculations on the gravity side.
Hmm.
So in the gravity side, I have a black hole with temperature, okay?
Yeah.
So the thing is you can show that, like I said to your friend moments
Facu,
before. Sorry?
my Facu.
Yeah. Like we assume that the gauge theory in the boundary is a theory of finite temperature. The thing is, the black hole is related to a gauge theory with finite temperature. So when I do those stuff with a black hole with temperature, I'm actually saying that the theory I'm assuming it's related, it's some theory with finite temperature, some gauge theory with finite temperature. And I assume that this theory is QGP. Oh, sorry, is QCD. So I'm actually describing some QCD system, which is the quark gluon plasma, which has temperature and densities. And I'm assuming that the gravity side with a black hole describes the thermodynamics and all the dynamics of this plasma, by assuming that the theory on the other side of the correspondence is a theory that describes the plasma. In other words, the QCD. I'm assuming that this somehow reproduces QCD on the other side of the correspondence. It's not exactly
Okay.
QCD, but assuming this. So like you
Okay.
work on this black hole temperature and stuff right here, but you don't actually say that it's a black hole here. you just assume that all this engineering you are doing over here in the gravity side with black hole and everything. Everything you calculate the Hawking temperature. This is the Hawking temperature for this problem over here. You assume that the other theory is QCD, and the temperature and the things you calculate on the gravity side, all these parameters over here, like this zeta, Q, chi over here, all this stuff, you calculate in the gravity side. But you are assuming that the other side of correspondence that does the stuff represent are somehow the plasma in the QCD.
Okay.
That's
Thank
how
you, Ayrton.
that's how you see the whole picture of the thing.
Okay.
You don't
Thank
know
you.
how it works, how this side of QCD works, but you calculate everything in the gravity side. And this is really nice. And people get this thing over here. So the interpretation of this picture over here, of this graph over here, is that somehow the plasma in the QCD theory goes like have this transition over here. So actually, that is not a black hole over here going a phase transition. What is going a phase transition? You are assuming that the quark gluon plasma you are trying to describe goes a phase transition like this. Okay, because all the parameters we are calculating, they just go to a specific point that go the same after this point. So you have like a critical endpoint over here, which describes a phase transition. That's how people interpret these results. Okay, so you don't actually for defining for to be more clear, people don't actually see this as a black hole. You do the calculations as a black hole, but the thing you are interpreting is QCD, and the thing related to QCD you are interested in this case, the quark gluon plasma.
Yeah. Perfect.
Yeah,
Sorry. Yeah, we are taking you too much time, but we are learning a lot. Thank you.
okay, I'm just going to describe this in the model. So I'm gonna finish right now. I'm going a little quick right now in this. So basically, I want to use this model, this Einstein-Scalar model in the deep inelastic scattering. So I don't have to go through all this. The thing is that since deep inelastic scattering is done in zero temperature, I don't have a black hole anymore. This is the thing now. So all the things I'm gonna say to you right now, what are the things I did, and it's all new. It's not done anywhere. So it's my contribution to this field is what I'm gonna say right now. So in zero temperature, you don't have a black hole anymore, and you can just do the stuff you did before. So you got equations of motion like this, and you can have a master equation. You have to solve for some boundary conditions, and with this boundary condition, you get the A and B functions of your space-time over here. Okay. So all the things I did before, I'm gonna do that again for zero temperature, and this potential over here, it is chosen like to reproduce lattice QCD results. So when people do, actually this potential over here was used in this model for the quark gluon plasma. And the proposal for me when I worked with the professor in the US was to use this, like forget about this term over here. Just this action over here, this potential being the one they used in this model. Okay. So we have this potential in which they reproduce lattice QCD results, and they got this nice result over here. Why not apply this to the deep inelastic scattering problem? So this is the potential they used with these values over here, and my contribution was to use this model here to the deep inelastic scattering problem. So I go through all that again, the Poshinsky prescription, I get the photon field and everything. Steps really similar to what I did before. Uh, things differ a little bit over here because the question of motion, because the model is different. And we go with the fermions again and everything. And yeah, a little bit different right now, the terms over here, because yeah, I'm using a different action and different space-time. But we got all over that again. We have like a Dirac-like equation of motion in which we decompose like the Fermi field into left and right chirality. and I'm going to work on the equation of motion, and I get this one, the equation 70 here, in which this I have a potential. This potential over here is different from this one. From this one over here, it's a different potential. It's a potential related to the equation of motion for the fermion field. You see that this potential is different from the one they used for the model in the QGP problem. So there are different concepts, and I work the equation of motion with this potential. I solve it numerically and everything, and I get these solutions for the fermion. I go through all that again with the Poshinsky prescription, the fermions and the photon and everything. Work out the hadronic tensor. After that, I just have to work out the interaction action, and I get something really similar to what I showed you before, these integrals, the IL and IR, which in my model goes like this, like equation 76, with something different over here. So I get these new terms over here in the integrals. And I work out with this, I can just work out the hadronic tensor and everything, and I can read off the F2 function I'm interested in. So the F2 function I get is this one. It's really similar to the deformed ADS model, but this time I have a factor over here of 2. The integrals are a little bit different, right, in this time. And I have some parameters here which I can use, which is this G effective here, and the mass of the final state. The mass of the final state, but inside the integrals, I have some M over here because they come from the equations of motion here, right? Because they go into the potential. This M over here, this capital M, is just the mass of the fermion in the bulk, like in the ADS space. While this M over here, Mn, is just the mass of the fermion in the boundary of the ADS space. So these are different masses. Okay, so in my model, I can work out the mass in the bulk, right? And I can get F2. So the results I got for my model, for the model I use, it's not like the Einstein Delta model is mine. It's like I was inspired by it. But when I applied it to this, I got these results over here. So I tried to do the best fit to describe the proton mass, but the thing is that this model over here, I don't get the same mass for the left and right chirality over here. So you see that even though I use like this M, this is the best M value of the fermion bulk mass that describes this right chirality mass over here. That is the one closest to the proton mass when I try to solve numerically the problem. So these are the best values I get these masses over here, but I don't get the chance to have the same mass for both. I have different masses for the left and right chirality. So the thing is that I get this result over here for 0.65. And when I do the same for the 0.75, I get this result. And the best one that I found was for the 0.85. So with these parameters over here, I can get these results, and this is the best one I get. And the conclusion from this is that you see, like this one, even though like the experimental points over here, they are not just as well fitted as the other holographic models. The thing that the model I used to do is that they still reproduce the same behavior that the F2 function does for the other holographic models. So they go like this, like a decrescent F2 function, right? So the conclusion I draw from this is that even in the model I used, the model worked best for 0.85, like for large values, for high values of the X parameter. So this is interpreted like if you have like a X value of 0.85, it's like it's still in elastic process, but it's more like a scattering of the entire proton rather than quarks and gluons. So that's why the interpretation is that you have a scattering of the entire proton rather than quarks and gluons. And the conclusion I can draw is that not all such models can be devised really well to describe F2. You saw that the other models I talked about, they can be fitted really well to experimental data, but like a holographic model like the one I used, it did not fit that well, but it is really interesting that it really gets close to some experimental points over here. So you got this point, you got this point over here, and this point gets close to this. So the thing is, even though it's not a good model for deep inelastic scattering, you even so get really close to experimental data. You reproduce some previous behavior of other holographic models. And yeah, that's the thing I wanted to tell you today. And I hope you appreciate the presentation. That's all for now. Thank you.
Thank you, Ayrton. Thank you for the talk. Very appreciated. I will start the recording and